see it.
All right. I'll begin with a word of prayer. Dear Father, we thank you for this day, and I thank you again for these students. I just pray that you help us to understand just a little more about topology, particular sequences, and some various concepts that are somewhat challenging but interesting. In your name I pray, Lord Jesus. Amen. So I guess I should share with you guys. So I don't know exactly what it was, but Daniel was, my son Daniel was making a cup, and originally it was just the red thing, and then he was like, could I put water in it? And I'm like, no, you can't, it's going to leak out. And he's like, oh, okay. And then he'd come back to me, and he had it full of like blue bricks. I was like, oh, that's so cool. Can I take it to school and show people? And he's like, yeah, sure. I'm like, okay. And then, for some reason, he's like, and then tomorrow I'll put feet on it. And I was like, oh, okay. And then he took it away from me and put feet on it. So now it's got feet. And I think these may be, I'm not sure if this is some kind of rocket blasters. I don't know if these are antennae or eyes.
Let's say horns.
Horns, maybe? Yes, it's got some kind of in there. I'm not sure what that's about, but I'm hoping that Daniel will continue to make us more creations as the days go on. I will share more. We'll see.
Not bad.
Yeah. So the next, we talked about projective space and coordinates on those and such. Ideally, I'd like to find some kind of homework where you could calculate something in there, but the problems in the section are good. I think it would be healthy for me. I mean, something I want to do is to work out this problem on Grassmannians. It has the T symbol, foreboding T symbol, page 97 to 98. But it's an important construction. It would be good for you guys to work through it now when you've got a little bit more time in your life, as opposed to you're in the middle of a busy graduate semester and you got to figure out what on earth the Grassmannians are. I mean, it's a little bit so. Anyway, section 5.5 is on locally compact spaces. Here's the definition. A topological space is locally compact if every point has a compact neighborhood. Okay. So you can, pick a point, you can find a neighborhood, and for that neighborhood, any open cover of the neighborhood, there exists a finite subcover of the neighborhood. So it's, as he says, open sets in Rn are locally compact, right? Lots of things are locally compact. Proposition 5.25, every closed subspace in a locally compact space is locally compact. The product of two locally compact spaces is locally compact. So, local compactness behaves at least as well as compactness, right? Like these theorems are also true if the space is globally compact. That's a good question. Does global compactness imply local compactness? My guess is yes. I don't see that said here yet. Oh, there it is. Straight from the definition, we have that any compact space is locally compact. All right, yeah. Well, I'm silly. I mean, of course. Right? I mean, a neighborhood's a subset. Any subset of a compact space is once again compact, right? Because the finiteness of the open cover condition descends to this in a natural way. Excuse me. Every point in a locally compact Hausdorff space has a local basis of compact neighborhoods. Read that again. Every point in a locally compact Hausdorff space has a local basis of compact neighborhoods. Well, that's very nice, right? Local basis. What does local basis mean? Do you guys remember?
Is it like a basis of a neighborhood, or no?
I think that's right. So the proof involves Wallace's theorem. You know, the Cartesian product of compact is compact again, right? And then finally he's got a theorem about identifications. For if he has an identification, f going from x to y, and then if you have a locally compact Hausdorff space Z, then you can take the function that you're given, cross the identity map, and that will be an identification from x cross z to y cross z. So there's a locally compact Hausdorff allows us to make nice new identifications from old identifications, I suppose, if you look at it. Although I think as a general principle, producting things is not hard, it's the quotienting which is the tricky part. Alright, then he has a section on the fundamental theorem of algebra which I would encourage you guys to read. Like I was saying, I think that the general point here is, it all goes back to the extreme value theorem. You know, when you study complex, you'll see a proof of it in there, Jess.
Mm-hmm.
Like, there's a very concrete, explicit. There's several. Yeah, right. There's like in a decent complex analysis book, there'd be like 4 or 5 different homework problems that allow you to prove the fundamental theorem of algebra. Basically, every major tool we come across in complex analysis allows us to prove it.
That's cool.
Yeah, and the proof isn't much different from what we see here. These elementary symmetric functions, we have seen that those are interesting beasts. But I'd rather not get into that here right now. Yeah. I'm not sure what axe he's grinding here in the rest of this section. Like he proves the fundamental theorem of algebra at the start of the section, right? And then the last, he's got like elementary symmetric functions. He gives this map, which is a closed identification. Now this may have important uses to like classical algebraic geometry. He's talking about taking, you know, the quotient of Cn by what is this sigma? It's what is it? It's what is sigma defined to be? The sigma n. Oh, sigma n action. What is sigma n? Sigma n is a subgroup of the homeomorphisms of Cn, I suppose. This defines a representation of a symmetric group, huh? Well, this is doubtless useful, but I'm going to go on. I think that this is something you should look at. Keep this in mind. I would look at this from time to time. As you come back, I would read this again in your like second reading or something. You know. All right, so that brings us to chapter 6, which is on sequences. And so there's some terminology in here. Excuse me, definition.
Quick question, what does he mean when he uses like the little arrow, like the flipped arrow, like at the end of a lot of his sections and stuff? Like he did it just in the fundamental theorem and then he does it in future things. What does he mean by that?
Where tell me
like this. Well, he just got it there. Like, I don't know, 103, like at the top. He labels sections and he even labels chapters with it. What does he mean by that?
This is in the preface.
What is it?
In order to help teachers decide what to skip, I indicated with the symbol, the arrow.
Okay.
Oh,
It's like,
I was ignoring the arrow. I just decided to skip it on my own. I guess
so, yeah,
the author and I have similar ideas about what we should skip.
There you go.
I don't think I see that symbol anywhere else. He doesn't say that much. Wait, let's see.
There's one of the chapters called Intermezzo, where it's a whole chapter that he says to skip.
Yeah, well,
And chapter 8, more topics in general topology.
Yeah.
That's kind of
Huh. Oh, that's kind of funny. That was the first one, really. I mean, I skipped some of the exhaustion by compact sets because I got exhausted there, but I'm sorry about that. That wasn't right. Alright, I'm getting the backtrack here. So, Definition. A topological space is said to be second countable. What does it mean for a topological space to be second countable? If the topology of X admits, what does it have to admit? A countable basis of open sets. All right, you guys are going to have to help me remember these terms as we go on in this lecture, because I tell you, this stuff does not stick in my brain. This chapter more than any, the terminology that's used in this chapter, I understood it once. I'll understand it again as I'm telling it to you, but 10 minutes after I've said it, I will have forgotten it again. So it's up to you guys to remind me. And I'm not saying that's how you should be. I'm just saying that you should learn it when you're younger than I learned it, so you'll remember it. What does countable mean?
Means either with bijection to natural numbers or some finite set.
Right. So, yeah, some people would say countably infinite if it's the natural numbers, but countable includes both, I suppose. I guess terminology varies a little bit, but yeah, that's a good definition. A space with this property is also said to satisfy the second countability axiom. All right, so his example is, let's see here, how about the reals? How can you show that reals are countable? What would you use as a basis of open sets? Could I use, would these work? Or what does it take to be a basis of open sets? What does that mean?
The basis constructs the entire set itself. Right.
There's a condition. It was a theorem. Yeah, you're right. I always go back to that theorem we had, that if if you satisfy this condition in the theorem, like for example, one of the theorem was if I had an open set U, right? One, let's say, and I had another one open set U2. If so I should use a different color or something. And how's it go? In order for it to be a basis, what do we have to have? The intersection, right? There has to be, I think the way it had to be, there had to be something in the basis, right? Like a W, which contains the intersection of open sets, right? Something like that. Or was it that the basis had to be inside the intersection? I forget.
It's inside.
So my pictures, so there actually has to be a W, which is up in here, right? Like that, like it's inside the intersection of arbitrary open sets. So these guys aren't going to work. They're not nearly small enough or refined enough to be a basis of open sets for the reals with the metric topology, at least. So what could we use?
Rational numbers.
Right. So what if you take open intervals, say from P to Q, where P and Q are rational? It has always been interesting and bizarre to me that the rational numbers are as large as the natural numbers. Right? There's a bijection between the rationals and the natural numbers. It's weird. That's so weird to me, but it's true. Cantor's map, right? You can list the rational numbers in their reduced form, basically reduced form, and then kind of use the numerator and the denominator in a sense to order them. And then you never run out of natural numbers. So once you have a linear ordering like that, it's just a matter of counting. Details are annoying, but that's basically it.
So is it the same for complex then too? No?
complex numbers are just as big as the reals. Rn is just
They're not.
as
They're
big
not
as R.
twice as big as R.
Mhm.
Really?
So there's a distinction between the dimension,
What?
right?
No, never mind those.
No, this is a very, very, it takes us a while. So dimension, right, versus cardinality. Right, so like, let's see here. I guess I should put R over here. C, Q. There, that should do it. I don't know how it's Z. Z mod PZ. Now, dimension is totally vague in this context because what kind of dimension am I talking about? Cardinality is talking about enumerating, like it's comparing a bijection between these sets and some given standard set.
Yeah.
So I think let's see, how's it go? Reals, I think Aleph not, right?
Aleph 1.
Oh, Aleph 1? I forgot, man.
Natural numbers still.
Is it up or down?
Aleph?
Down.
Down.
And then this is also Aleph 1.
Aleph 1, yeah.
But this one,
Aleph not.
Aleph not. Because that's the same
There's natural numbers.
as natural numbers. Well, anyway.
For some reason, for complex, I just want to say like it's squared the number of real numbered, like the cardinality of the reals.
But the thing is, I could just as well put n,
Yeah.
or even m by n. Wouldn't change anything
Yeah.
in terms of the cardinality. But the
Yeah.
dimension, of course, would be n. Here, the question is, do I mean real dimension or complex dimension, right? Like the real dimension,
It would be 2 MIN, right?
yeah, 2m, I think 2m by 2n, right? So 4mn. The real dimension of this doesn't even make sense. It's not a real vector space.
Yeah.
Ahem. Not a real vector space. Ah. No, I'm just kidding. Well, I'm not talking about that.
I mean, it's a vector space over itself, right?
It is a rational vector space of dimension
One.
1, right? Now, in fact, let's talk about rational. Forget about that. Let's talk about rational dimension. So the dimension here completely depends on what your notion of spanning is. What's your field of scalars?
Mm-hmm.
So if the field of scalars is rational, this is infinite dimensional. This is infinite dimensional, and so is this.
Yeah.
Because it takes infinitely many rational numbers to build real numbers.
Basis, yeah.
But on the other hand, this is not a rational, right? But down here, the dimension of this, of course, would be, well, if you take that as the field, this is one-dimensional, right? If I took this and took like n tuples of it, then this would be n-dimensional. I'm talking about the dimension mod PZ, like that. And then the cardinality over here, on the other hand, is what? P, right? For n equals to 1. And then it's p to the n
Yeah.
for n tuples. But it's something that it takes people, like, it sneaks up on you, you know? I've met a lot of people who understood both of these, but didn't realize that it never kind of hit them there's a difference. You know, but it happens to all of us at some point or another.
I'll ask you more about that later.
Yeah, sure. Where was my... So anyway, I will... So I guess the question is, why is that a countable basis, right? Well, you're taking rational endpoints. Pairs of rational numbers is still just as big as the rational numbers, is still just as big as the natural numbers. It's a countable basis. And so there you have it. The reals are, in fact, second countable. It's, well, I don't know, almost any concept we come across in here, surprise, surprise, the real numbers fit. All right. His example 6.4 is kind of powerful. Well, 6.3 is nice. He says basically a subspace of a second countable space is second countable. Because it's again this like, it's essentially the same as the compact. Like a subspace of a compact space is compact because the finiteness condition descends to the sub. So like that again. And also the product of two second countable spaces is still second countable. So that's also nice to know. Then what? Next definition, separable. Topological space is called separable if it contains a countably dense subset. I should probably start numbering these. This is definition 6.1, the first one was. This is definition 6.5. As usual, we are in Minetti. A topological. It's funny, I had some Italian graduate student in physics asked about what the prerequisites were for topology, and I was like, lucky for you, you don't have to read the translation, you know? I mean, I have to think that this book is probably even better if you could read the Italian, right? I mean, I don't know, just guessing. Topological space is called separable. Separable if it contains a countable dense subset. All right, so what is, you guys have to remind me, what is dense? How do we define dense?
Closure is the entire space.
Ah. That seems worse. You never have figured out the marker problem here. You know what I'm going to do? So, in other words, D dense in X if the closure D is equal to X. All right. I'm going to build, another of my things to do over break is to build myself some like marker trays. You know, right?
A lot of projects.
Okay, all right, so let's see here. Topological space is called separable if it contains a countable dense subset. Is the reals, so the reals are separable, right? The rationals are dense and the reals and countable. Aha. He doesn't even say it. Must be too obvious. All right, fine. Lemma. 6.6. Every second countable space is separable. Lemma 6.7. Any separable metric space has a countable basis. What's wrong with me? I'm spelling metric with an X all of a sudden. Metric space has a countable basis. All right, let's see here. So how do you prove every second countable space is separable? So he actually just does it. He just builds the stupid thing.
Constructs a dense subset.
Right. He's basically, I'll write down here. He's like, let beta, be countable basis for X, all right? Okay. And then for any open set U, in the basis of open sets, choose a point P, U, and U. All right. And then he says, okay, so then the set, he says the set of such points E, calls it E, equals to PU such that U is in the basis, the countable basis, is countable. And dense because it meets every basis element.
Could you give like an example of like a countable set that isn't separable?
A countable set which isn't separable.
I'm having a hard time like visualizing that.
Wouldn't that not be possible? Because you could just take the entire set to be the subset, and
Yeah.
Yeah,
And
every
closure
countable
is
its
just
closure
itself.
would be itself.
Yeah. Therefore, all
So that wouldn't be
countable.
possible.
So all countable sets would be separable.
Yes. Yes. Because
Okay.
every countable set is second countable.
Okay.
But you notice here X doesn't have to itself be second countable to be X doesn't have to be countable to be second countable. Like the reals are not countable.
Right. But if it's countable, I think it's
Mhm.
second countable. Right.
Yes. So the example that I think Jess is really looking for is something that's uncountable,
Not separable.
but not separable. Yeah. No. I don't know right off the top of my head, honestly. I'm trying to remember. There's got to be a good example. I think. Well, he has not. He's not given a counterexample in here. Sometimes finding a counterexample of some of these things can be much more work than,
Only one that satisfies it.
you know. But that's a good list of things to look for an example. Let's put that on our list of things to look for. Find a, what do we want? We want a uncountable. We decided has to be uncountable. X, which is not, right? What do we got?
Not separable.
Not separable. Meaning what? It does not allow, it does not contain a countable dense subset.
I can't like.
Well, the reals are separable, and that's what's messing with your intuition. Is your intuition is reals, right?
Yeah.
It's not bad. It's just, you know. There's a whole book which is counterexamples in topology, which is nothing more than these kinds of things, page after page after page. I think I have it.
Really?
Yeah.
Yeah, I think I saw that.
There's counterexamples in analysis. That's not what we want. Oh. See it right off, but I will put that on my list of books to look for. It should be here somewhere. Okay, I'm gonna go on here.
Sorry about that.
No, that's don't be sorry. That's it. I mean, that's the whole point of this course is to ask these kinds of questions.
I don't want to take up too much time reading lecture though.
No, that's what this is for. I mean, there's no more important thing to do in here than ask that kind of question. That's ideal. Whether or not we find the answer right now, just to be aware of the question is something. Let's see here. I think the proof of this may be instructive. Let me look at that for a bit. How do we prove this? Any separable metric space. Well, metric space, well that's nice, right? Has a countable basis. So what he does here, he's like, okay, let XD be a separable metric space. All right. And choose a countable dense subset E of X. Why can we do that?
Because it's separable.
Because it's separable, so we have a countable dense. Right, okay. He says it's enough to show that the countable family of open balls, and so here's what he's going to use for his countable. He's going to say B is equal to the ball of radius, well, basically E is not the radius, E is the center point. So he's using center point and then radius. E is in E, and N is a natural number. So the the fact that it's countable is kind of like it's in your face. Well, it's not quite in your face. I mean, you have, let's say, quote unquote, the natural number worth of these things at each E, right? But the thing is, how many E's are there? Well, E is being selected from E, right? Where E is countable. So it's something like the countable Cartesian it's like something like the countable union of countable things, but that is countable. So this is a countable basis. The question is it a basis, right? Is that a basis? It's countable, but is it a basis? So what he says is, he says, take U open and take X an element of U, then choose N such that what? The ball at X with 2 to the 1 minus N is a subset of U. Now, why can you do that?
Because X is an interior point.
Right, yeah, exactly. U is open, X is an interior point. And we know before that the balls of various diameter form a basis for a metric space, right? And we're here, so that's you have to be able to find something in here inside you if you make this small enough. And of course, as n goes to infinity, that gets very small. So you can choose such an n. All right. Now here's this next point. As E is dense, right? There exists. So what does the density of E give us? There exists an E in what? What intersection? The intersection of
E and open set.
right.
Open ball.
You know, he has just 2 to the minus n here. So why would he do that? Why would he drop it one more? Well, I guess not. I mean, he has 2 to the minus n. Not, there's the 1 is gone.
Right, I mean, it's going to be like half the radius, so.
So I guess here's a picture of you, right? And here's x, right? So that's this one maybe, right? And then what does E look like? E is, I don't know what E looks like. It's some, what does E look like?
Well, it's inside the open ball with half the radius. Because it's 2 to the minus n.
So my picture's wrong, alright.
I mean, it was fine.
But I want to make a bigger one. So E is, where is E? E is,
Inside the open ball of radius 2.
oh, E is in here,
Yeah.
huh? Well, E doesn't have to be in there, does it? E could be, couldn't E look like this?
Oh, the set E, yeah.
The set E could look like
Right.
that. Now, you're saying the point E is
Right.
like in here. Yes, I'm sorry. Legitimate confusion, right?
Right.
And then, so this, I need another color.
Well, E's dense, so it's gonna.
Yeah, you already said E is a subset of it. Well,
Right.
where's X at?
Uh-huh. Uh-huh. That's right. So what did you say?
Oh. Well, E's dense, so it wouldn't really look like that.
Uh-huh.
But,
Do you mean? Wait.
E is dense. It is capital E.
yeah. It's at the beginning.
Okay. Oh, right. E is. Oh, yeah.
So,
You're right. That's not even the right picture. E is. It's.
I mean,
It's
kind
you know,
of
it's like
kind of
the
contains it, but not really.
big E.
Kinda
It's like chemtrails. It's like the World Bank. It's everywhere, man. It's like it's out here. There. Shout out to those conspiracy folks. All right, there we go. So that makes sense that there would be that E there. Then what? Sorry. So symmetrically, X also belongs to the ball B E to the minus 2n, right? Okay. 2 to the minus n. So from the triangle inequality, we have that. Here's the punchline. Triangle inequality finally gives us that B. Why is it so hot in here today? I need an air conditioner. If I had an outside window, I'll tell you what. Let's see here. Maybe I'll just cut a hole over the engineering classroom and route. Dump my heat over in there. Maybe they can talk about the thermodynamics of it. With me. Stand by that fun. Let's see here. So that shows, for triangle equality, you have that as a subset of that, as a subset of that, which then shows you what? That it's a basis, right? Because there's a smaller one of these guys inside the intersection, right? As needed. All right. Now, I realize in my life there are certain questions I'm going to have to be exceedingly careful about dense things. And I'm saving some of my energy for those questions. There are, of course, nice proofs in here. He next develops the L2 over the reals, the set of real sequences which are square summable, and he shows that that set is in fact separable and has in fact a countable basis. He builds that countable basis here. How he looks at what does he do? He says, consider the countable set E, subset of L2R, of eventually null, in other words, eventually zero, rational sequences. So he takes truncated rational sequences, and then he argues that, in fact, those form a countable basis for the set of, like, convergent square summable sequences. So that's a nice example. Example 6.8.
What do you mean by square summable?
Oh, that simply means that basically it's the infinite 2 norm. Sequences A1, A2, A3, da, 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 and so on and so forth forever and ever, such that that's less than infinity. The set of all such sequences is denoted L2R. So that makes, for example, this makes A an element of that.
Wait, so is that a different notion than like the LP norms we went over?
No, that's well.
Because I don't remember it being like an infinite sum. So
Right,
I guess
well,
this is just sort of analogous to that for sequences.
We
right?
were talking about. So there, I think what you're thinking about, we were talking about finite dimensional vector spaces. So we had a fixed dimension. So our sequences were finite. I mean, in some sense, a vector space is a space of finite sequences. Right? I mean, whatever the dimension is. Slight abuse. But the difference, I guess, would just be that it didn't go to infinity, it just went to n.
Okay,
Which is an
so it's
unfortunate choice
just
of letter here. But
similar, except we're treating it as an infinite dimensional vector,
yeah.
essentially.
Right, well, those norms that we talked about, the 1 norm, the 2 norm, the p norm, the sup norm, those are still defined for sequences, and they defined respectively like L1, L2, LP, and then the maybe L infinity. I forget what the name of it is, but
I think that's a synonym for the sup norm, right?
yeah. So that's what's up over there. Let's see here. Proposition 5.9. But that is a good question. Proposition 6.9. In a second countable space, every open cover admits a countable subcover. In a second countable space, every open cover admits countable subcover. What if I just give everybody an A this semester in physics? What would happen then?
There's a lot of people wanting to take it next semester.
Yeah, that's true. What if I
That'd
just
be really-
fail everyone? Sorry, I digress. In a second countable space, every open cover admits a countable subcover. Does that make sense?
It's kind of it's broader than compactness. Instead of a finite subcover, it's a countable subcover.
Oh, okay. I was about to say, isn't this just compactness? But duh, no, because. Oh yes, yes, yes. All right. Very good, very good. I'm gonna read the proof. He says, let X have a countable basis beta. Consider an open cover A. For every X and X, choose an open set UX and A, and an element BX and B, such that X is an element of BX which is contained in UX. So he's like, okay, so then the open family beta prime formed from looking at all these B sub X's, well, that's a subcover of beta, so it's countable. And we can find a countable subset E of X such that beta prime is equal to a collection of BX such that X is an E. Whence UX such that X is an E is a countable subcover of A. So pretty much just looks at the countable basis and the open cover which is given. And just picks from it a countable subcover. I guess the basic point here is in a second countable space, right? You've got this countable basis of open sets. So you've got that. It's everywhere, and you can just kind of use that to do these things. I mean, that's what's going on here intuitively. All right, definition. 6.10. A topological space satisfies the first countability axiom. Oh my goodness, not another term. A topological space is first countable. I'm pretty sure this is first countable. He says satisfies the first countability axiom, but I think we could safely say it's first countable.
Yeah, it says right after.
Oh, if first countable. If what? Every point admits a countable local basis of neighborhoods. So second countable had to do with, it was a global concept, right? It's a countable basis of open sets for the whole topology. First countable is like essentially the same idea, except focused on a point, right? Like if you look at a particular point, then for that point you can find a countable local basis of neighborhoods, but hey, you can do that at each point. So first countable is sort of a local version of second countability, right? And then his first lemma 6.11 is that metric spaces are first countable. Metric spaces be first countable. All right, good to know. And his proof is pretty simple. He's like, let X be an element of a metric space, X, then open balls. You can use open balls centered at X of radius 2 to the minus n, such that n is a natural number. That will give you a local basis of neighborhoods around X. And as you can see from the n dependence, it is countable. Nathan, you could even tell me the cardinality proving map here, right? Psi of be x comma 2 to the minus n is equal to?
And
Very good. There you go. There's your bijection n. Yay. Okay. Sorry. So yeah, that's a local. It is a countable. You know, I guess if you don't follow it immediately, we do still, of course, need to prove that this forms a local basis of neighborhoods. But I think we actually proved that before when we introduced the term local neighborhood basis. We looked at the example of metric space, I believe, back when we did that, and we showed that. Okay. So the more interesting aspect of this is, think about this, right? And this is a much more difficult question, right? Suppose you're given an abstract topological space, right? And you're asked the question, is this topological space a metric space in the following sense? Is it possible to construct some wacky distance function, right? Some by whatever method, I mean, who knows? Your imagination's the only limit. Is it possible to find some state? Where's my note to self? Find stones. All right. Take that. Is it possible to is it possible for the space to be metrized? Is it a metrizable space? So this is something, because what this says is that if you have a space, right, and if your space is not first countable, right, if it doesn't have this property,
It's not metric.
yeah, no way you could find a metric on it to reproduce the topology as a metric topology. Now, of course, the point set, strip off the topology, you could make it a metric space probably. I think there's always some sort of stupid tautological metric you could give that would give the indiscrete topology or something stupid like. But anyway, if you're stuck with it's too late to topologize, as we were talking about. If you're stuck with the topology you already got, you're stuck with a topology which is not first countable, then you cannot realize it as a metric topology. And he gives the example of this cursed lower limit line, to which I lost many hours in grad school on a particular homework, and I'm still a little bit bitter about. Because I just don't think it's interesting. I mean, it's an interesting counterexample. For example, this. So example 6.12, he reminds us the lower limit line is not metrizable because he shows you that there's a countable open family that's a local basis around A, and he shows that it doesn't contain. What's it have to do? I've already lost my place. Every point admits a countable local basis in neighborhoods. Well, he shows that this one doesn't, basically. Okay. Theorem 6.13 concerns exhaustion by locally compact. So you have a second countable. Suppose you have a second countable. I can erase that, right? Yeah. So theorem 6.13. X second countable, locally compact, Hausdorff space. Right. There exists an exhaustion of X by compact sets. So yeah, like K1, subset of K2, subset dot 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 dot. And these are these cover. They cover X, all right? and they also have the requirement that the nth one of these compact sets is contained within the interior of the n+1th compact set for any n. Proof doesn't look too bad. But I'd really rather spend our time talking about sequences in here. Let me just kind of glance over the proof a little bit here. What makes this different than when we talked about a little bit about compact exhaustions before. That was, and where was that? That was 4.7, right? An exhaustion of a topological space is a sequence of compact subspaces that covers and has that containment by the interior of the next one condition. So, oh, okay, so that section he just gave examples of them, right? And he talked about the one-to-point compactification and the compactification being Hausdorff if and only if every point in X has a compact neighborhood. Okay, I see. So he just really introduced the term back in that other section. Here we're finding that if you have a second countable locally compact Hausdorff space, there exists an exhaustion of X by compact sets. So that's something new. It says that, you know, and the example he gave in that previous section of this happening was like R2, for example. Well, R2 is what? Is it R2 locally compact? Yeah, it's not compact, right? This notion of local compactness is important, right? Because a lot of the spaces you care about are like more or less vector spaces or something like that, right? And those are not compact because they go on and on. And yet, if you focus in on a locality, right, then you can always kind of put it inside some ball, bound it, then that behaves as a compact thing. And so Hausdorff, well, that's just kind of everything for us. We're not sneaky enough to look at non-Hausdorff stuff too much. Not yet, anyway. So I guess to my taste, this is a very natural theorem. What this says, it's nice. Any questions about what this is saying? Again, the principal use of this is if you have these conditions on your space, then you can assume the existence of this compact exhaustion, and then if you can prove something for the compact exhaustion, you can prove it for the whole space, and sometimes it's easier to work with something that's countable as opposed to something that's not. So, I digress. No, I'm not digressing. What am I talking about? Sequence. Finally, sequence. What is a sequence? Actually, this section on sequences, I don't know. Is there anything here that you guys don't already know on sequences? I mean,
Those on Rails probably. No.
I guess the difference is how the sequence is defined. I mean, how the limit point is defined in terms of neighborhoods in a topological context, as opposed to how it was captured for you guys in. I mean, you probably have more or less the Calc 2 definition in Rails right now, right? Like,
Yeah.
sequence converges if for every epsilon greater than 0, there exists a k such that for n greater than or equal to k, the epsilon value of a sub n minus l is less than epsilon.
Yeah.
Modulo inequality or something, but
Yeah.
yeah.
Such a long time ago.
So this is a little bit different, I suppose. So we should look at it. But what I really want to talk to you about, all right. Sequences. So what is a sequence? Sequence is just a function, right? from the